Okay, in this final little video about these 11 problems in physics, I'm going to go over my speculations about how can we really pull everything together. So I'm actually going to go to this one. Of course, I haven't tied everything together, but I dream of it. I've been dreaming about it since I started working with quaternions as owner of quaternions.com, and only recently was very troubled by a property I realized of quaternions, the real number line, which is probably the first deep math concept anybody ever learns, like in second grade or something, about, you know, there's positive infinity, there's negative infinity, and zero sitting right in the middle, okay? And basically all of mathematical physics uses it, okay? And when I was thinking about quaternions dealing with problems in space-time, it's like, yeah, I got four real number lines. I got these four zeros. Isn't that great? And it's like, no. Those zeros don't have a darn thing to do with each other. And you say, well, I'll impose some ideas of measure between them, and I'll be able to, you know, say there's some relationship. It's like, no. This is about topology. This is how things are connected. And to me, zero is hugely important because it's the observer. Everyone's an observer of their own life, okay? And you've got 1, 0, and, well, you get to choose your coordinates, but you've got one past, you've got one future, okay? And you got one left, you got one right. If you decide to use left and right, up and down, you know, but you could go spherical if you wanted to. And I said, no, they've got to be 1, 0, one observer. It's got to be dead center. And so I drew it dead center, and I drew these eight lines going out of it, and it was like, oh no. You know what that means? I've got no minus signs, people. I don't have a real line. There isn't one. Okay, there'll be an idea eventually of opposites, you know, this one takes away from that one, that sort of thing, but drawn this way and connected to that 1, 0, you can't just, so I'm coming in from the left and I'm continuing on to the right, because there are a bunch of different rights you could go to, right? Which one, if you come into 0, which one do you go out on? This is really uncomfortable for me, okay? And I've been dealing with this for a few months. I'm not sure how to proceed, you know, in terms of programming and all these kinds of things. I'm trying to incorporate big messages from physics right at the start of this thing. So, for example, 1's a big deal, because to me that's like the light cone. And if you're beyond the light cone, well, I mean, you exist, okay? If you're beyond my light cone, you exist. I just can't know about you at that moment. Okay, ever. You know, it's unreachable. It's about causality. So it's kind of like I'm trying to come up with a causality topology and then figure out how to program animations from there. That's all I got to do. I'm not sure I can, but that is my direction. Okay, and so how does that affect, say, something like the fundamental forces? Well, I'm working off the quaternion group QA. And I'm thinking that if you're going to describe something outside yourself, outside your 0, where you hang out, right? Then you probably want to normalize those numbers. And if you kind of normalize something that's a quaternion, well, you automatically get the group SU2, because the SU2 is the unit quaternions, okay? And if you normalize quaternions, well, that's going to have a U1 in it, like automatically. Now, this actually makes U1 and SU2 like too close to each other for most theoretical physicists. What they want to do is think about them completely separately. I don't blame them. Look, I don't blame. It makes a lot of sense to think about them separately. And as a matter of fact, there's some technical thing they have to do, like putting little flags next to their groups, so because U1 is formally a subgroup of SU2, to say, no, you're really different. Well, maybe that's the way unification is. Things are too close, but too bad. Maybe there's a way of dealing with that. And that's a kind of subject that just, it's probably too hard for me. But it's my hope, okay? Because if I have this quaternion group and it's all normalized, I'm going to have these 8 kind of basis vectors that are all going to have a normal 1, which sounds, which at least echoes things that are said with the group SU3. Now, quaternions are never going to be the group SU3, okay? It took me a while to accept that, okay? Maybe we don't want SU3. Maybe, you know, because the strong force has this odd property. It's called confinement, okay? It's like I can go, quarks can go the speed of light. So you figure, well, then they're going to fly apart from each other whenever the hell they feel like it. And the answer is no. They actually can't. They can't separate. It's like, why? Because of confinement. Okay, yeah, okay, because of confinement. Why is confinement there? That's the kind of question you of course they can't answer it. I mean, it's really hard to figure out how you would work on it, okay? Confinement was a hard enough idea to come up with in the first place. Now justifying confinement, okay, that's really difficult. So my hope is it has to do with, okay, I've got these 8 directions to go. 4 are kind of like in the past and 4 are kind of like in the future. And maybe if I think of all 8 of them together, well, I can't have the past separate from the future. So it'll never happen. If I somehow try to come up with a force, which is, I should say this, forces are not like you would think about it, somebody pushing on stuff, okay? No, forces for physicists, I should say, forces for physicists are symmetries. There's like, oh, that's, look, imagine you were here. Could you tell if you were, and we rotated it. Would you care? You go, no. Okay, that's what you say, conservation of energy is like. Come back in a year. I won't have done a single thing, and I've conserved energy the whole time. Okay, they're about doing nothing. Okay, and so the strong force, despite its name, is about doing nothing with 8 things. Okay, and maybe this has to, and somehow it's confined. And so maybe it has to do with dealing with normalized group Q8 and not being able to separate the past from the future, because then you wouldn't have now. I mean, I hope that sounded vague and imprecise, because I get lost pretty quickly in this subject. But that's where I'm dreaming. I'm dreaming of one group that has all of these properties. Oh, but what about gravity? Please mention it, because when we deal with the standard model, we never mention it. So I will. And to me, gravity is about who decides what is 1. Okay? Well, here's the deal I'm going to make you. I get to decide what is 1 for me. You get to decide what 1 is for you. And we are both at peace with that. But there's this third clown who's going to compare your notion of 1 to my notion of 1, okay? And what the clown is going to come up with is he's going to say, actually, your notions of 1 are different. As a matter of fact, his notions of 1 for the space part stuff get a little larger, but his time-like 1 gets a little smaller than yours. And, 1 appears in the standard model all over the place, a normalized, it means the norm is 1, a complex number. A normalized, mean the norm is equal to 1, is SU2. Oh, strong force involves a bunch of things that have a normal 1. And what I'm saying is, well, yes, as far as you are concerned, it's always 1. As far as I'm always concerned, it's always 1. You get into a gravity field, and the third guy is going to compare our notions of 1, and when he compares our notions of 1, he's going to say, something funny happens to the space part of your notion of 1, which is actually the inverse of what happens to your time 1. So, who knows if that has a chance of working, but at least it's all centered around a group and really having a profound understanding of said group. All right. So what about the arrow of time? Arrow of time comes about for me when you really treat everything as a quaternion and you just don't allow anything to just say, oh, it's really small, it's zero. No, nature never forgets nothing. I mean, she doesn't have that option. She doesn't work that way, okay? And when you do that, you can see the terms that everybody says, you know, that term's symmetric in time, and they're right, okay? They're not saying something wrong. They're just not mentioning that if you actually write everything down as a practice, there'll be terms that aren't like that. Now, they're really small. They are joke small, okay? I'm not here saying then they're really big. They are teeny weeny is just, it's not an appropriate word. It's just to how stupidly small they are. But here's the thing. We are dealing with an even stupidly, that's not a word, all right, really monster big number of particles. So when you're dealing with 10 to the 23rd particles, you know, that little thing, you add it up that many times, and it's obvious. It's obvious there's an arrow at a time, and it's obvious there are a heck of a lot of particles, and it's obvious that, well, maybe they make an effect once you add them all up. At least that's my hope. And then I guess my biggest dream is for the day when we actually have visualizations of all this algebra. Because this algebra, for all of humanity's time, will be beyond most people. Okay? In fact, a lot of it's beyond me. And I have tried to get a very fancy education. But pictures have reach. They really do. And if we can say, instead of saying, here's this nasty equation, if we can say, here is some pictures, and can't you see? I think people are going to say, well, actually I can. And actually, I think they're going to say, and what about that little detail? And I'll have to stare at it a long time, because I'll probably see it also and go, I wonder what part of physics that is. I wonder what piece of algebra caused that little thingy that they are totally correct in pointing out. And it might take me a long time, or somebody else smarter, to say, oh, that is that physics phenomenon. You know, I can imagine that happening. Because I have done some animations of quaternions. They've always surprised me when I get sad or depressed about my situation, about work, life, all these balancing acts and stuff like that. I will sometimes just stare at my animations and go, oh, that's fun, okay? It's an effort to open up a door that is closed to most of humanity, and if and when we open it, it's just going to be a most remarkable time. It really will be. At least that's my hope. So thank you for your time.